Good evening, students. Welcome to the session 9. And this session 9 is of the chapter of electrostatic potential and capacitance. And the topic is the effect of dielectric on the capacitance of a capacitor. Now, I have drawn one figure here, which is a capacitor consisting of two conductors, that is conductor. I have depicted these two conductors as 1 and 2. So these two conductors are placed apart by a certain distance, say d, and the area of we can say the surface area of these two conductors is A, that is a capital A. So, and let us assume that the charge on this conductor 1 is Q, and the surface charge density is sigma, and the charge on this conductor 2 is minus Q, and the surface charge density is minus sigma. So the capacitance of this parallel plate capacitor, which has got a vacuum or free, or you can say there is a free space or a vacuum between these two plates. So the capacitance of this parallel plate capacitor having vacuum or free space in between this space between these two conductors is given by epsilon naught A divided by D, where A is the surface area of these two conductors, or you can say the conducting plates, and D is the separation between these two conductors. Now, what I have done is I have inserted one dielectric here in between this space between these two conductors, and now we will see what will be the effect of this dielectric on the capacitance of this capacitor. So when we insert a dielectric in the space between these two conductors of this capacitor, the dielectric will get polarized. Okay, the dielectric gets polarized. Okay, the dielectric gets polarized because of the electric field. Okay, the electric field is directed from the positively charged plate towards a negatively charged plate, and because of the presence of this electric field, this dielectric gets polarized, and because of this polarization we can assume this dielectric equivalent to you can say two charged sheets having the surface charge density say as minus sigma p and sigma p. Okay, now minus sigma p means this is the because of this positively charged this conducting plate, a negative charge would be induced on this side of this dielectric, and because of this negatively charged conducting plate, that is the conductor number 2, a positive charge will be induced on this side of this dielectric. So because of these induced charges, let us assume that the surface charge density of this dielectric on this side, that is towards the positively charged conductor, is minus sigma p, and the surface charge density towards the negatively charged conductor is sigma p. Now, because of this dielectric getting polarized, the electric field now you know that this electric field E will be given by sigma minus sigma p divided by epsilon naught. ठीक है, अगर ये आपका डाइलेक्ट्रिक नहीं होता, then the electric field was equal to sigma divided by epsilon naught. But because of the this dielectric and it getting polarized due to the presence of an external electric field, the electric field now can be written as sigma minus sigma p divided by epsilon naught. Now second thing is, since sigma is proportional to sigma is proportional to sigma minus sigma p, we can say that, or we can write sigma is equal to k sigma minus sigma p, where k is a constant, means I have just removed this proportionality sign by a constant which I have written here as k. So sigma is equal to k times sigma minus sigma p, or we can say that, or sigma minus sigma p can be written as sigma upon k. Okay, this can be. Now the potential difference V across across this capacitor can be written as V is equal to E into D. So E is equal to, here is sigma minus sigma P divided by epsilon naught into D. ठीक है. Now as I have just told you that the sigma, I will be writing it here, that sigma is directly proportional to sigma minus sigma p, or sigma is equal to k sigma minus sigma p. So it implies that sigma minus sigma p is equal to sigma upon k. ठीक है. So हम इस sigma minus sigma p की जगह पर I will be just substituting this sigma minus sigma p by sigma divided by k. So we can write as sigma divided by k epsilon naught into d. Now sigma is the surface charge density. So we can write this. We can replace this sigma by this q upon a. Q divided by a k epsilon naught into d. So this is the potential difference across this capacitor, ठीक है, due to the insertion of a dielectric. ठीक है. Now the capacitance C is equal to Q upon V. So we can write it as C agar is equal to Q upon V, or we can say that it will be equal to Q divided by this term. So finally what we will get is Q divided by QD divided by A K epsilon naught, or you can write it as A K epsilon naught divided by this Q and Q will cancel, divided by D. ठीक है. Now this term, that is K epsilon naught. K epsilon naught जो है, this is called the permittivity of a medium. ठीक है. This epsilon naught, this epsilon is the permittivity of a medium, and this is I'm just writing it here as, this is the permittivity of a medium, and permittivity जो है, की जो डेफिनेशन है, permittivity is the property of a material which opposes the formation of electric field um, across it. So ये जो this permittivity जो है, this can be substituted in this equation. Now, first of all, I just want to write the definition of permittivity. That permittivity, it is the property of a material. It's the property of a material which measures the opposition to the formation of electric field. ठीक है. So now this K epsilon naught is equal to epsilon, which is also written as epsilon naught into epsilon r, where epsilon r जो है ना, this is called the relative permittivity of a medium. So, or in other words, we can say that so K epsilon naught is equal to epsilon, which is equal to epsilon naught epsilon r, where epsilon r is the relative permittivity of a medium, or we can say that it implies that K is equal to epsilon r. Now K is basically the dielectric constant of this dielectric, and it is also known as the relative permittivity of a medium. So the relative permittivity of a medium is also called the dielectric constant of a medium, and they are governed by this relation, that is K epsilon naught is equal to epsilon naught epsilon r, which is equal to epsilon. ठीक है. So if we know the relative permittivity or the dielectric constant of a medium, we can means we can substitute, or we can just if we know the relative permittivity of any medium, that is if we know the value of epsilon r, then the permittivity of that medium can be known by using this relation, that is this is equal to epsilon naught epsilon, and this epsilon naught जो है, this is the permittivity of free space. So the multiplication, that is permittivity of free space into the relative permittivity, is equal to the permittivity of a medium. So if we know this epsilon or if we know the value of this dielectric constant K, then we can know the permittivity of any medium. So now let's come to this equation, that is C is equal to A K epsilon naught, and where K epsilon naught is called the this K epsilon naught is equal to epsilon, and this epsilon is the permittivity of a medium. It's the permittivity of a medium. ठीक है. So इस इक्वेशन में द C इज इक्वल टू A है, इसमें हम लिख सकते हैं K एप्सिलॉन नॉट की जगह पे एप्सिलॉन A अपॉन D. ठीक है, वेयर एप्सिलॉन इज इक्वल टू एप्सिलॉन नॉट into K, or it is also equal to epsilon naught into epsilon r. ठीक है ना, where epsilon r is the relative permittivity of a medium, which is also called the dielectric constant of that medium, or K is equal to epsilon R. So ये मेरा एक इक्वेशन बन जाता है, that is C is equal to epsilon A upon D भी हो जाता है. Now from this equation we see that now अगर आप इसको देखेंगे, so C is equal to A K epsilon naught upon D. So A that we can also write as C is equal to we can write it as A epsilon naught upon D into K. And this epsilon naught A upon D is the capacitance of a capacitor when the medium between these two conductors is either vacuum or free air, which is denoted by C naught, that is equal to K. So C is equal to C naught into K, where K is the dielectric constant of a medium, and it is also known by epsilon R, where epsilon R is also called the relative permittivity of a medium. So K and epsilon R are the same thing. So the capacitance of a capacitor which is filled with a dielectric in the space between these two conductors is given by C naught dot K, where K is the dielectric constant of that particular medium. And so we can see here that since the value of this dielectric constant is more than 1, since K is greater than 1, therefore we can say that the capacitance of a capacitor increases when a dielectric is inserted into the gap between the two conductors of a capacitor. यहाँ से आप देख सकते हैं कि यहाँ पे जो कैपेसिटर की जो कैपेसिटेंस है वो इंक्रीज हो जाती है if we insert a dielectric in the gap between the two conductors of a capacitor. ठीक है? So this is all I just wanted to discuss in this session. In short, we can say that the effect of the dielectric on the capacitance is that the capacitance of a capacitor increases if the dielectric is inserted between the gap of the two conductors of the capacitor. So thank you very much for joining this session, and in the next session we will be taking up another topic in which we will be discussing about the series and the parallel combination of the capacitor. So I hope you have understood this lecture, and the next lecture will be uploaded maybe by tomorrow. And so till then, have a nice day. Bye.